Last day of the week. So I don't have any classes tomorrow. We don't have any labs this week, and nobody has any classes or school Thursday or Friday for Thanksgiving. I do have my office hours today at the tutoring center if anyone's interested, and then that's the last thing I'm doing this week. Anybody have any homework questions you'd like me to go over? Anything that was confusing? All right, so we're done with conservation laws and we're going into kind of the start of the last topic. So this new topic is rotational kinematics. And you also hear people talk about this as angular or rigid body kinematics. I'll probably go back and forth a little bit between angular and rotational. Remember, the meaning of kinematics is that we're not dealing with the causes yet. We're just describing the motion. What's the difference? The first thing we need to talk about is the difference between a particle and a rigid body. This is the first time we've not been talking about particles and we've been talking about rigid bodies. So remember that one of the definitions, when I talked about what a particle is, I said particles have no length dimensions. And because they have no length dimensions, there's no way to talk about orientations of a particle. You can't tell if it's spinning. It doesn't have like a face to tell like, oh, it's facing this way now, it's facing this way now. You can't tell what a particle is looking at, okay? Particles have no orientation. Rigid bodies have length dimensions. And you can track their orientations. So, for example, this could be a rigid body, okay? And so at a later time, it could be, why did I draw something so hard to draw at a later time? At a later time, it could be like that, let's say it has a thing here, and now this thing is over here. Since it has all these, it has different locations on it, you can tell which way those locations are facing. And so what we're going to be doing calculations for is for bodies that have length dimensions like this, what are the things that affect how they're oriented or how fast they're spinning and things like that, okay? The thing that makes this a little confusing is that rotational kinematics is closely related to circular motion. So it's related to circular motion, but you need to try to keep these two things straight. So this is circular motion. This object. So we're thinking of this thing as a particle, and it's moving around a circular path like this. And is it spinning as it goes around? We have no idea, and we don't care because it's a particle. okay? So this is circular motion. Rotational motion, we aren't talking about particles. We're talking about bodies that have dimensions. And so in this case, what we're talking about is like if you have this board and this is like a hinge or a pin, something it can rotate around, I'll call it a hinge. And generally I'm going to refer to that as the about point. That's the point it rotates around. And this rigid body can be spinning around that point, okay? So I'm going to do a little like interpretive dance representing this. So right now I'm in circular motion, you know? Right now I'm in rotational motion. You can do both, you know? Like I could be in circular motion and spinning at the same time. But particles, we don't know and we don't care. So we're getting into the calculations of rotational motion. But why are they related? This is where it gets a little confusing. They're related because choose any point on a rigid body that's rotating, and that point is in circular motion around the about point. Right? That point you can think of as a particle, and that particle is following a circular path around, that's not a good circle, but it's following a circular path around the about point. You see that? So we're going to do a lot of going back and forth between what we know about the rigid body and what we know about the individual points. Like for example, if this thing was spinning around that hinge at a certain rate, you know, say 100 RPM or whatever, you know, a certain rate, we could calculate velocity and acceleration vectors of individual points, okay? So the reason that they're related, the way they're related, is when a rigid body is rotating, each point on the rigid body makes a circular path around the about point. And the about point is that hinge or whatever. Bless you. Okay, so to talk about rigid body rotation, rotational motion, first we have to define two new quantities. And those are angular velocity and we're going to represent that with the lowercase Greek letter omega. It looks like sort of a round W. And second, the angular acceleration And we're going to represent that with a lowercase Greek letter alpha. Looks like a goldfish going to the left. And one thing to remember about these if a body is in rotational motion, the angular velocity omega and the angular acceleration alpha are the same for the whole body. So these values represent the entire rigid body. But the velocity vector, like we're used to thinking of velocity, and the acceleration vector, like we're used to thinking about acceleration, are different for every point on the body. Okay, so we'll get into a lot of questions where I'll tell you something about the angular velocity and angular acceleration, and then I'll say, what's the velocity vector of this point? What's the velocity vector of this point? What's the acceleration vector of this point? It makes sense if you think about, think about one of these circular paths. So this outer circle, think about the motion of that point. The velocity vector, since the path of that object is this circle, the velocity vector is tangent to that path in the direction of motion. Okay? The acceleration vector, well, I can't draw that for sure because I didn't say what the angular acceleration is. But, you know, it'll have a centripetal part and a tangential part, right? What about this part? What about this point here? You know, at this instant, what's its velocity vector? Well, the little circle is its path. So the velocity vector is tangent to that path in the direction of motion. And so, you know, at that instant, those 2 points are moving in opposite directions, even though it's the same body. Okay? All right, any philosophical questions yet for anybody? You sort of know that's the case. Like if you think of like taking a bicycle wheel, holding a bicycle wheel that's like wet and spinning it, water will be flying off in all these different directions. Well, it's flying off when it leaves, it's moving the direction of its velocity vector at that point. So you know water will fly off that way on this side, that way on this side. That's because all these points have different velocity vectors. Okay, angular velocity. So let's start with that. So the angular velocity omega. So what this is telling you is how quickly and which direction a rigid body is rotating. The units of angular velocity are angle divided by time. So you could imagine doing this in degrees or in numbers of full revolutions or in radians. It turns out that radians are going to be the most useful. The SI units that we're going to use for this, the ones that we're going to see almost all the time, are radians per second. And radians are kind of like, radians are the pure mathematical description of an angle. So if you're using, let's see, when do you need to use radians? If you're doing any kind of calculus with this stuff, your angles have to be in radians. There's no other option for it. I want you to notice that even though we're going to be doing all these calculations in radians, you can leave your calculators in degrees because we're not going to be using any trigonometric functions. Because we won't need sine and cosine for this. When I talked about the velocity vector, I said that the magnitude of the velocity vector was the speed, and the direction was the direction the object is moving. So now for the angular velocity, the magnitude is how fast the orientation is changing. And the sign is what is going to give us the direction. And that is positive if the body is rotating. This is kind of backwards, so pay attention to this. It's the opposite of what you would expect. But positive is counterclockwise. And negative is clockwise. Okay, so just like with a vector, you can think of it as having a magnitude and a direction. The direction is whether it's positive or negative. Okay, so let's think of relating this to, units we're more used to. Let's say that you have a propeller rotating at 2,000 RPM. That's rotations per minute. And let's say that it's rotating let's say it's rotating clockwise. What's its angular velocity? Well, how many full rotations it makes is just a way of telling you what the change in the angle is. One rotation is how many radians? 2 pi. And then 1 minute is 60 seconds. And so then from there we can just do it like a usual unit conversion. It's going 2,000 RPM, so its angular velocity is going to be plus or minus 2,000 rotations per minute. One rotation is 2 pi radians. One minute is 60 seconds. And so you come up with plus or minus 209.44 radians per second. Now we have to think about the sign of it. It said that this propeller is rotating clockwise. Clockwise is negative, so the angular velocity is negative 209.44. We can relate the full body's angular velocity to the speed of any point on the body. So there's a relationship between the angular velocity of a body and the speed of a point on the body. And that is that the speed is equal to, I'm going to call this capital omega, I'll tell you what that is in a second, times r, okay? So this v is the speed of the point. This is a capital omega, and that's the absolute value of lowercase omega, of the angular velocity. So just drop the negative if it has a negative. And then r is the distance from the about point to the point, the point of interest, the point that you care about. So let's do an example, and we'll see for a given rigid body what we can figure out, how we can figure out the velocity vector of a point. Okay, so let's say that we have this rotating board. And let's say that the length of the whole board is 2 meters. And the about point is here, and let's say the distance from the end of the board to the about point is 0.4 meters. Okay. And let's say this is the point P. If the board has an angular velocity of negative 20 radians per second, that's spinning pretty fast. What's the angular velocity, or the absolute value of the angular velocity for something that's making 1 revolution per second? This is kind of a way to visualize the size of these things. Remember, it's in radians, so 1 revolution is 2 pi, which is about 6.3, say, So something that has an angular velocity magnitude of 6.3 is going around 1 revolution per second. So this is, a little more than 3 full revolutions per second. So that's really, you don't want to get in front of that. Okay. But we want to calculate, what's the velocity vector of that point P. Well, remember that point P is in circular motion around the about point. That's just how it always works. So it's following a circular path like that. The sign of the angular velocity is negative, so is it rotating clockwise or counterclockwise? Clockwise. So this point is moving that direction along that circular path. Okay. So what's the direction of the velocity? Well, it's tangent to that path in the direction of motion. So it's that way. Now we know the direction, we just need to figure out the speed, the magnitude of the velocity. So the speed is equal to, just ignore the sign of the angular velocity, 20, times the distance from the about point to the point you care about. What's the distance from that black dot to the red dot? 1.6. Yep, 1.6. And so this is 32. The units come out to be meters per second, like you would expect for a speed. Why do the units come out that way? I said that the angular velocity and the angular speed are radians per second. But remember that radians are just kind of a pure mathematical description of an angle. So that's really just a guide for you. It really is not a unit at all. What we really have is, negative 20 1/seconds. And so you have 1/seconds times meters, and you get units of meters per second. Okay, well, we have that the speed is 32 meters per second. We've figured out that the direction is down. And so the velocity vector of that point is 0, negative 32 meters per second. Any questions about that? It's not hard. It's just a lot of new terminology to sort of digest, and once you start doing a couple of these problems, hopefully it'll just sort of sink in. Why did I use this this funky Greek symbol here? Well, that's a capital omega. So just the same way that I'm using a capital V to be the magnitude of the velocity vector, I'm using a capital omega to be the absolute value of the lowercase omega, the angular velocity. And I'm going to do the same thing for the angular acceleration. So all of these capitals, what it means is just the magnitude of the value that has a direction. Okay. Let's just think about another point for a second. What if I did the velocity here? I was saying that the velocity of every point, the velocity of every point on this body is different. This whole body is rotating clockwise, like this. So what's the velocity at this instant of that green dot? Well, the velocity vector is tangent to that circular path in the direction of motion. So up. So now for this point, well, let's give this a name too. Let's call this the point B, I guess. So what's the velocity vector of the point B? We know the direction now. We figured that out just visually. The speed of that point is the absolute value of the angular velocity, so 20 again, times the distance from the about point to the point we care about. What's the distance in this case?
0.4.
Yep, 0.4. And so you get 8 meters per second. The direction is up, and so the velocity vector of that point B is 0, positive 8. So even though those 2 points are on the same body that has the same angular velocity, the directions and the magnitudes of the velocity are 0. Without doing a calculation, what's the velocity vector of the black point?
Nothing.
0, right, because that R value is 0. So no matter what the angular velocity is, there's no velocity of that point. And you know that from, well, I don't know, maybe they took these for most of you out of the playgrounds before you were kids, but they used to have these sort of death trap things made out of like thick steel that you would spin around and it would spit kids off and, you know, everyone's bleeding and stuff. It was...
Merry-go-round?
Yeah, right. Those things that like so hard to get going. But if you can picture being on something like that that's rotating, if you're on the outside, it's really hard to hold on. It's hard to stay on. But if you can get yourself into the middle and hug the thing at the middle, you don't feel much of anything. That's because when you're way on the outside, your speed is high. When you're close to the about point of that rotational motion, your speed is close to 0. Okay, so now angular acceleration. And I'm going to denote this with the Greek letter alpha, lowercase alpha. Alpha is the rate at which the angular velocity is changing. That's not a surprise, you know, because the acceleration you're used to is the rate at which velocity is changing. So this works just the same. So alpha is the rate at which omega is changing. The units for alpha are angle over time squared. And the SI units then are radians per second squared. Just like with angular velocity, the direction of the angular acceleration is positive if the angular acceleration is counterclockwise. And negative if the angular acceleration is clockwise. Well, how do you know if it's clockwise or counterclockwise? This is going to look familiar. If omega and alpha have the same signs, or have yeah, signs, same directions. Is the body's rotation speeding up or slowing down? Yep. So let's say the rotations are speeding up. And if omega and alpha, oh, I missed the same, that's important. And if omega and alpha have opposite signs, the rotations are slowing down. Okay, when we were talking, so when I introduced angular velocity, then I told you a relationship between the translational, the velocity vector v of a point on the body, or I guess the speed on the body, and the angular velocity. Now I'm going to give you a similar relationship between the angular acceleration and the tangential acceleration of a point on the body. So hold on. Relationship between the angular acceleration of a body and the tangential acceleration of a point on the body. And the relationship is the magnitude of the tangential acceleration. If we were talking about including the direction in this, it would have a vector symbol over it. So this is just the magnitude of it, is equal to capital alpha times r. You know, the magnitude of the angular acceleration times r. Well, capital alpha just looks like a capital A. And then times r, which has the same meaning as it did before. So this A tan is the magnitude of the tangential acceleration vector. Capital A is the magnitude or the absolute value of the angular acceleration. It just means you chop off don't worry about the sign, just use the absolute value of it, chop the sign off. And then r means what it did before, the distance from the about point to the point. That's easy to remember because these two have basically the same thing. You know, look at the form of this relationship between the tangential acceleration and the angular acceleration. And then look at the form of the relationship between the speed and the angular velocity. It's just the angular thing times that r. In both cases. Okay. So let's do an example again. This time, let's say we have a wheel rotating about a point at the center. So that center point is the about point. And let's think about the velocity and acceleration of 2 points on the body, okay? So this here is the about point. That's physically like a hinge or a pin that this is spinning around or something like that. Let's call this point A and this point B. If the body has an angular velocity of positive 10 radians per second and an angular acceleration of negative 20 radians per second squared, we want to calculate the velocity vector and the acceleration vector at the points A and B. I need to tell you how far away these points are from the, bless you, how far these points are away from the about point. So let's say that the whole thing, the radius of this wheel is 0.4. And that A and B are halfway out from the center to the end, okay? And let's start thinking this through. We'll do it as two totally separate problems just to get practice. This point A, what does its motion look like? Well, we know it's in a circular path around the center. And we know that its path is the same path as B. It's just in a different spot around this path at any given instant. Based on the sign of the angular velocity, which way is this point A moving around that circle, clockwise or counterclockwise?
Clockwise. The acceleration.
No, the velocity.
Oh, counterclockwise.
Counterclockwise, yep. So it's going this way. We'll worry about the acceleration in a second. So if that's the path, the direction of the velocity vector is tangent to the path in the direction of motion. So like that. That's the velocity of that point A. The speed at that point A is equal to the absolute value of the angular velocity, so 10, times the distance from the about point to A. What's that distance? 0.2, yep. And so this is 2 meters per second. Well, we figured out visually or intuitively or whatever that the direction is up. So now that we know the magnitude, the velocity vector of that point A is 0, 2. Or you could just think of it as 2 pointing in this direction. Okay, so now we're going to go to the acceleration of that point A. Remember that the acceleration is made up of two parts, a tangential acceleration and a centripetal acceleration. We're going to use the angular acceleration to figure out the tangential acceleration of that point. But remember, the centripetal acceleration just comes from the speed. So we don't need to know anything about the tangential, angular acceleration to find the centripetal acceleration. We're going to use other stuff for that. But let's think about the directions of these. So the centripetal acceleration always points toward the center. We know that from talking about circular motion in the past. What direction does the tangential acceleration go? We know that it's parallel to the velocity. Well, if these two are opposite, the angular velocity and angular acceleration, then we know that the tangential acceleration has to be in the opposite direction of the velocity. So the tangential is this way. We know that these rotations are slowing down. Are you with me on that? No? Okay, that's all right. Forget it. No, just kidding. So based on the fact that angular velocity and angular acceleration are opposite, we know it's slowing down. That means we know that the tangential and the velocity are also opposite each other. So first, let's figure out the sign of the tangential acceleration, the magnitude of it. So this is equal to the absolute value of 20 times r. What's the distance from the about point to that point A?
0.2.
Yep. And so this is 4 meters per second squared. Well, we already figured out that it's pointing in the negative y direction. So the tangential acceleration vector of this point is 0, -4 meters per second squared. And now the centripetal acceleration, we don't have to do anything new with this. This is just equal to v squared over r. V we already calculated is 2 meters per second, so 2 squared over 0.2. And so that is 20 meters per second squared. We've already figured out intuitively that that points in the negative x direction. So the centripetal acceleration vector is -20, 0 meters per second squared. And so finally, the total acceleration, just add up those two parts, and you get that the total acceleration of the point A is -20 in the x direction, -4 in the y direction, meters per second squared. Or, you know, basically something like this with a magnitude of, what's the square root of 416? I don't know. Anyone have a calculator? What's the square root of 416? Oh, yeah, so 20.39 meters per second squared, sort of in that direction, if you want to visualize it. Okay, that is the velocity and acceleration vector of this point A. Now let's do the same thing for B. This time, why don't you take a few minutes and see if you can work through all these steps. Okay, so for the point B, I didn't draw the whole body, I just drew the circle that it's moving on, you know, so here's the point A, here's the point B, but that's still 0.2 meters from the about point. The angular velocity says it's moving this way. That means that the velocity vector is this way. the tangential acceleration, since it's slowing down, has to be opposite of the velocity. The centripetal has to be toward the center. To get the full velocity vector, now we need the speed. And that's equal to the absolute value of the angular velocity, that was 10, times the distance from the about point to B, that was 0.2. And so you get 2 meters per second. And so the velocity vector is in the negative x direction, so that's -2, 0. And now for the acceleration, the magnitude of the tangential acceleration is the absolute value of the angular acceleration, 20, times r, 0.2, and that's 4 meters per second squared. The picture shows us, we've already figured out that that's in the positive x direction, so the tangential acceleration is 40 meters per second squared. And now the centripetal acceleration the magnitude is v squared over r, so that's 2 squared over 0.2, which is 20 meters per second squared. We figured out that it's in the negative y direction. So the centripetal acceleration vector is 0, -20. So the total acceleration is, add up the two parts of the acceleration, 4, -20, or in other words, that's going sort of like this way with a magnitude of, what was it, 20.3? Okay. And this is an acceleration just like you're used to. So if you say that you were doing this calculation because you noticed there was like a mouse sitting at this point, and the mouse had a mass of 0.05 kilograms. I'm not good at guessing the mass of a mouse, but let's say 0.05 kilograms, okay? Now you have this acceleration. The net force is 0.05 times that acceleration. And you could start doing forces on the mouse or whatever too. Anybody have any questions about that? So I'm giving you 3 problems to work on, and a lot of time, like not due till the end of next Tuesday. So just, you're going to be going through steps very similar to this, just trying to sort of ingrain it in your head. Okay, that's all. Have a good Thanksgiving.
Yes.